Okay, this third unit, I call it stoichiometry just because the title that the government gives is way too wordy. Technically, it is quantitative relationships and chemical changes, which doesn't mean anything to anyone. But let's talk through those words actually. What is a quantitative relationship? Quantitative involves, yeah, numbers. And so our goal in this unit here is to be able to calculate how much we have, either in reactants or in products. But we need to be able to calculate how much. And I'd like to begin with this very basic idea of a question. Let's say that for whatever purpose you have, I don't care what your goal is, but you need to make 20 grams of silver. Now, I'm not just saying about 20 grams. I'm saying I want it to be exactly 20.0 grams right on the dot. I don't want you to make me 22 grams and I have to get rid of some. I don't want you to make me 18 grams and I'm coming up a little bit short. Does that make sense? And I want it to be silver solid, not, say, silver liquid. Not that we'd normally expect that. Does that make sense? Um, have you guys watched Breaking Bad? If you've ever seen Breaking Bad, Walter White was very much a perfectionist in that show because like every setting had to be absolutely perfect for him to make the perfect quantity of his crystal meth, which kind of we're not doing in this class, but I mean, as a chemist, you don't like just go close enough, right? Like you actually have to be very, very precise in terms of all of your quantitative values. Okay, and so what I want to do today is talk a bit about some of the things you want to consider if this is your question, and then by the end of the day, hopefully we'll be able to talk about, well, this is how you would produce exactly 20 grams of silver solid. Just like in Breaking Bad, he wants to produce exactly whatever his amount was, all right? So what I'd like to do before I get to that question then is I want to talk a bit about what we've learned so far. Up until this point in your chemistry lives, really the only things that we can use would be, say, like a chemical equation. Okay. You guys have learned about balancing chemical equations before. My question I have on this slide here then is, well, what sort of information does a chemical equation tell us? And I'd actually say it's very limited. It tells you things like the reactants. I know what to start with. I know that I need solid copper. There's another thing I know. Not only do I know what the reactants have to be, but it also tells me the state of matter required. This says I need solid copper. In a way, this is like a recipe. If I use liquid copper, maybe that wouldn't work. You know what I'm saying here? So it tells me reactants. It tells me states of matter. It also tells me one more thing. It tells me the ratios required. Imagine that you're in the kitchen and you're cooking. You know how you have a recipe? It would say that for every 5 eggs, you need 1 cup of flour and 2 tablespoons of sugar. Right? Well, what happens if you double the recipe? Well, then 5 becomes 10, and 1 becomes 2, and 2 becomes. You know what I'm saying here? What we really know is we know our ratios. Now, a chemical equation, though, writes it in lowest common terms. What it really says is that for every 1 copper you bring 2 silver nitrates. And when you do that, you'll get 2 silvers and 1 copper nitrate. But could we not upscale this in our heads and say for every 50 coppers we bring, we would need 100 of these? You'd get 100 of these and 50 of those. So to answer kind of my initial question, what does a balanced chemical equation tell us? It tells us the stuff we use. I mean, stuff isn't the right chemical words, but we know what reactants and products to use. We get to know the state of matter, and we get to know the recipe in terms of like the ratios. That's not a whole lot though. From a practical point of view, there are so many other things to consider. Like, for example, does this reaction require a lot of heat? Does this reaction require a certain amount of pressure? Does that make sense? Does this reaction require a catalyst? If you guys have ever heard of a catalyst before. We'll talk about them more later in the year if you haven't. Right? And so I think my next slide actually talks about some of the things that are very practical questions to ask if you were a chemist trying to make something in a lab. So let me read through some of these practical questions. Here's a good one. Here's the first one. What do the reactants and products look like? It doesn't tell us that in a chemical equation, does it? Let's say that I am making a new chemical reaction, and I'm expecting to produce, in this one right here, silver. Do you know what silver looks like? Because that would be useful, wouldn't it? As your chemical reaction progresses, if you get a black metal, that could be silver. If you get a blue metal, you might think, something's going wrong here. You get what I'm saying there? But, like, does a chemical reaction tell you that? No. What apparatus is needed to contain the reaction? It doesn't talk about anything safety-wise. Is copper nitrate dangerous? Is it toxic? Is it likely to explode? Is it likely to be in a gas format that will escape on us? Chemical reactions don't tell us that. This is really the main focal point of what I want to talk about today. How much copper or silver nitrate should you use? If you're going to start with copper and silver nitrate, how much beginning recipe reactants should you begin with? Right? Should I start with 5 grams of each? Or should I start with 5 grams of this and 10 grams of this? Do we need equal quantities? It doesn't tell us that. It tells us molar quantities, but not mass. This is a really simple question, but did that silver nitrate really need to be aqueous? Let me use an example from the kitchen point of view. Let's say you're supposed to bake cookies, and you're supposed to use sugar in the cookies. But for whatever reason, you don't have sugar at home. And you're like, oh, I can't bake cookies. Well, if you're resourceful like my wife, she may discover, well, I can find a way around sugar, and instead of using sugar, she used applesauce. And it still worked. Right? Or let's say you're supposed to use butter, but you don't have butter, and instead you use margarine. Would it still work? You know what I'm saying here? That's a really resourceful question to ask because from a practical point of view, what if you don't have aqueous silver nitrate? What if you have solid silver nitrate? Would it still work? No, that's a good question to ask. Here's another important question. Would all of the reactants be consumed or would there be leftovers? Okay. By what I mean here is, let's say that you react some of A with some of B, and you're trying to make some of C and some of D. But let's say you accidentally poured way too much reactant B in there. From a cooking point of view, this would be like you use way too much flour. Okay? And so some of the flour does react and makes a muffin, but like then in the bottom of the muffin tin, there's a lot of excess flour, and it's kind of gross because a lot of the flour didn't bake properly because it didn't have enough egg and sugar to react with. You see what I'm saying here? What if there's leftover reactants? How do we deal with that? This is a really good question. How long is it going to take? Because some chemical reactions require 5 minutes. Some require years. Right? If I want to, again, use the cooking analogy, if I want to bake a cake, should I leave it in the oven for 5 minutes or for 2 hours? Because if I leave it for 2 hours, it might come out as a brick. You know what I mean? So there's another good question. Should it be, do we really need to time this reaction? Another thing this chemical reaction doesn't tell us. We know that all chemical reactions are either endo or exothermic. We have no information of that in that chemical equation. I'm in trouble. Sorry, guys. Okay, let me skip forward to the very, very last question because this was ultimately the point of the first question. Finally, the last one is how much product should you expect? Remember how my very first question was, how can you make 20 grams of silver? Right? This is an equation right here where I found a chemical equation. I found a chemical equation that it looks like it makes silver. Right? But back to my original question. How do I get exactly 20 grams? Not 21, not 15, exactly 20.
Right here. I was going to start at that one.
Sure, I can still handle that. Yeah. What's your bio test?
Hi guys.
I can help. No, I can't. Okay, so on this next slide right here, I've got a few things that kind of are related to the previous slide. Here's some things that we don't get in chemical reactions. that are worthwhile to know. If you were baking a cake, you would want to know what temperature to bake the cake at, right? And although we don't usually consider pressure when we're cooking, we should consider pressure in chemistry. So here's a couple of notes I've got for you. This is otherwise assumed. We usually assume standard ambient temperature and pressure, which is why we actually have the phrase SATP. Because it's kind of implied that if you're doing a chemical reaction, go with 100 kilopascals and 25 degrees Celsius. Because for the most part, that's about normal. Okay. Another thing chemical reactions they don't do is they don't tell you what's happening during the reaction. All we get in a chemical equation is what we had before we started and what we have after we're done. And for that like magical moment in the middle where all of the chemicals rearrange themselves and make something new, we don't actually get to see what happens there. Now, you can take entire courses in university on what's called chemical kinetics, which is basically about that moment in time where, well, how do the bonds break? What happens when these molecules rearrange themselves? Why do they occur? But to some degree, like we kind of miss that step. We just tell you what we start with. We just tell you what we finish with, but we don't tell you how it does that. That makes sense. It doesn't tell us time at all. Right? Chemical equations don't tell us anything about time. It also doesn't tell us whether it reacts completely. Because I've already given you guys one example in the first unit about how sometimes we need to put a little percentage on top here. You guys remember how we talked about strong and weak acids? Some reactions, they only react like half the time. And so when you're done, what you end up having is you started with some of this stuff. It made some of this stuff, but like some of the initial stuff just doesn't react for whatever reason. Only half of it reacts. Things that are strong react 100% of the time. So if you were to imagine like a bar graph of like the levels of how much stuff you have, when you begin, normally you'd have 100% of these guys and you'd have 0% of these guys, right? And as the chemical equation progresses, this bar goes down and this one goes up. Does that make sense? But we kind of assume that by the time we're done, that these guys become 100% and that these guys become 0%. But maybe that's not the case. And then the final thing, which is, again, kind of the point of where we're starting today, it tells you nothing about measurable quantities. Hence our unit on quantitative change. We're going to talk about, well, how much mass, how much liters, how much molarity, moles per liter do these things have? Because our chemical equations are very, not that they're not useful, but they don't necessarily tell us all of the information we need to be able to do a lab. So here's a few more assumptions we have. Again, I'm kind of just reading off my slides for now. I don't usually do this a lot. But we assume a few things when we write chemical equations. The first one is that we assume there's something called spontaneous. And this word comes up in one of our Chem 30 units a lot more. So I'll do my best to describe it right now without context. But spontaneous in chemistry does not mean fast. Spontaneous means that it occurs. You know how like I gave you that 100% over top of the arrow versus like a 5% on top of the arrow? Spontaneous means that it actually occurs. Okay? A non-spontaneous reaction would be one that occurs like 1% of the time. Does that make sense? Spontaneous in everyday life usually means someone does something like impulsively, or maybe they do it quite fast. You know, if you're a spontaneous person, you just decide to rush out and go do something without thinking about it. In chemistry, this is more about. In chemistry, this is more about as A turns into B, it happens. We assume that it actually happens. Okay, that's our hope. We assume that it actually happens because there are some reactions that on paper, I can write them on paper, and then I go to the lab and I take chemical A and chemical B and I react them together, and nothing happens. And you're like, but the recipe said it would work. Okay. I'll try to show you guys this more in the electrochem unit when we get to it. But second thing, we assume that reactions are fast. Okay, but that's not true because, like, for example, rusting is like super slow. But we assume for the most part that like the amount of time it takes for this chemical reaction to occur is very reasonable. It's not like the amount of time is going to be 10 years. But that's not true. Some could be 10 years. This one right here is kind of the same as spontaneous. I guess I should be more specific here. We assume that they're spontaneous, meaning we assume that they actually happen. But we also assume that they happen like at least 99, preferably 100% of the time. That's the other thing we like to assume, is that not only do these reactions occur, but when they do occur, that all of the reactants get used. When you're done, remember this like little bar graph thing I drew a little ways back here? I don't remember where it was anymore. But where like you start with 100% here, you start with 0% here, we like to assume that this goes down to 0 and this comes up to 100%. Okay? As the reactants get used up, all the reactants get used up and products get formed in their place. And then this one here doesn't make a whole lot of sense yet, I imagine, but the word we use is that they're stoichiometric. And what that means is that the coefficients stay the same. Because it's actually possible for your chemical reaction to change halfway through. I think I can explain this now. How can I do this simply? Okay, let's say that you had sodium and you reacted it with magnesium, no, not magnesium, iron chloride. No, hang on, one more time. I know what I want to do. Let's do it with iron and react it with sodium chloride. Okay. Here's where this kind of gets confusing. This would then, in theory, make sodium plus FeCl2. But what happens if, after a while of producing FeCl2, it stopped doing that, and eventually it started producing some FeCl3? Does that make sense? You know how iron has more than one valence state? So perhaps when we begin, it makes iron 2 chloride, and then later it makes iron 3 chloride. Well, that's going to change your coefficients. Does that make sense? Because in the first reaction, you need to do this, which means for every 1 iron, you use 2 sodium chlorides. But if it's not stoichiometric, what could happen is eventually it could actually form, you need to put a 3 here and a 3 here to make that work. So. Anyways, we assume that the coefficients stay consistent, and we also assume that multiple reactions aren't occurring at the same time, because that's also possible. I think I can give you another example here while I'm writing stuff out. Okay, this is what I was writing earlier, correct? Ideally, my iron would react with NaCl, and it would form FeCl2 or maybe FeCl3 and form sodium. But what if by accident, I didn't intend for this? What if the iron reacted with some oxygen from the air and formed this as well? Right? I intended for it to react with NaCl, but what happens if it was in an open environment? Isn't there oxygen around us at all times? So in theory, couldn't that iron accidentally also produce something else? So anyways, hopefully this gives you some ideas of things to think about from a practical point of view when you're trying to do chemistry, because there's so many more things than just take chemical A, chemical B, and just put them together, right? If we want to do it properly and do it exactly, there are so many things to consider. So today, I'm on my next slide here. I want to talk about 2 things to consider. Okay? The first one is about something called a net ionic equation. Often when we write equations, like I've shown you over the last few times there, we're given like the everything equation. But sometimes we can actually narrow it down and make it a little bit smaller and make what's called a net ionic equation. Okay. Let me start with my slides here. You guys know how some reactions require water? And the reason why it requires water is so that you can either dissociate or ionize things. What I want to do right here is show you an example of an equation where this is double replacement. We're going to take silver nitrate and sodium chloride, and we're going to double replace it into silver chloride and sodium nitrate. In this solution right here is something called a spectator ion. And the reason why it's been given the name spectator ion is just like a fan at a sporting event. It's on the sidelines. It did not do anything. It was there when we started, and it's still there when we're finished. And it did not chemically change in any way. Can you guys pick out the spectator ions? When we began, we started with nitrate ions. Can you guys see how when we were done, we still have nitrate ions? Does that make sense? Nitrate didn't change at all. It's a spectator. There's actually one more here as well. Yeah, sodium. Because when I began with sodium ions. And when we were finished, we still have sodium ions. Which leads to a really important question. Did this have to be silver nitrate? Or could it have been something else? For example, what if it was silver, it's already chloride, so what if it was silver bromide? If all of these were changed to bromine ions, and then afterwards, if I had bromine ions in here, would it have really impacted the chemistry that occurred? I'd say, well, no. Because at the end of the day, what I made that was new is I made solid silver chloride. That's something that's new that I chemical reacted. But these guys that started in solution and these guys that ended, they didn't really do anything. They're spectator ions. So often what we're going to do is we're going to shorten up some of our equations, and we're going to omit and get rid of the unnecessary parts. Does that make sense? So I think I have that on my next slides here. Okay. Here's a good example of a chemical equation. It's a single replacement. The first thing you'd like to do is you're going to want to dissociate or ionize anything that can break up into pieces. So for example, the zinc solid is still going to remain zinc solid. That you can't ionize. But I can totally dissociate copper 2 sulfate. I can break this guy up into copper 2 plus, and I can break it up into SO4 2 minus. So I'm literally just breaking this guy up into its ions. Does that make sense so far? Okay, on the other side of the equation, I have solid copper. That's not changing. But this thing right here, the zinc sulfate, I can break it up into zinc 2 plus, and I can break it up into SO4 2 minus. Okay, think more like math. What's on both sides of the equation? Yeah, the sulfate. It did not change, right? This sulfate right here that we began with, and this sulfate right here that I ended with, it is not chemically different. So what I could do then is I could cancel both of them. Does that make sense? And now what I'm left with is called a net ionic equation. And hopefully that name kind of makes sense. Net, because that's what's left over as after you've done your subtraction. Right? Like after you've finished doing your either adding or subtracting, whatever you do, this is what's left over. And ionic, because we've now broken things up into ions. So at the end of the day, really the bare bones of this equation is that you need some solid zinc, you need copper in an aqueous form. And when you're done, it'll produce copper. That's an alarm. Is it? Okay. What you're going to need is zinc in a solid form, copper in an aqueous form. That'll make copper in a solid form and zinc in an aqueous form. So this leads to a really important question. Did it have to be copper sulfate? I'm going to close that door. Did it have to be copper sulfate, or could we use something else? Let's say that I want to do this in the back of my lab, but for some reason I'm out of copper sulfate, just like how Melissa is out of butter. Could we replace the butter with margarine? Yeah, because really it didn't matter that this was copper sulfate. Let's say that it was copper nitrate. Well, by the time I was done, so long as copper nitrate gives me zinc nitrate, these guys right here, in theory, they like cancel. And so if my goal was, say, to make solid copper, it doesn't really matter who the other half of these equations is, because it's going to, quote unquote, cancel. Does that make sense? So we call it a spectator ion, something that's on both the product and the reactant side in the same form of matter, by the way. Okay. Some people would be like, well, hang on, can't I cancel these coppers right here? No, one of them was an ion, one of them was an atom. There's a huge difference there, right? It has to literally be the exact same. So this is one of the things we'll do, is we're going to try to make a smaller reaction type, just to break it down to the bare essentials. What do we really, really need? Okay, the other thing I want to talk about is some of the ways in which we do try to make those predictions. I started the class with the idea of, well, how do you make exactly 20 grams of silver? Well, now that we know that maybe we can play around with some of the reactants, maybe it didn't have to, like in this example right here, it didn't have to be copper sulfate, it could be copper nitrate. We still need to know the numbers, though. We still need to know how much to begin with. And so the general term for what we're doing here is called stoichiometry. Stoichiometry comes from the Greek, in case you care, I won't test you on this, but it comes from the Greek for measuring elements. So when you're trying to measure things in terms of either mass, volume, or concentration, those are the main ones we do here. Anything like that, we call it stoichiometry. Okay. And I'm going to start today by showing you two basic types of problems. We're going to go mole to mole and then mass to mass. And then later, I'm going to eventually show you guys how to go like, say, mass to volume. Or say from concentration to mass or something like that. We're going to make it so that these don't have to be the same as each other, and we're going to add in more ideas, but we're going to get there eventually. Like for today, I just want to keep it simple to start. So, I find it best to actually just hop right into an example. Here's my question for you. We have a chemical equation here where we're going to take aluminum oxide and we're going to decompose it into aluminum and oxygen. So here's my question. Let's say that I tell you that you have 3.34 moles of the aluminum oxide. The question for you then is, how much oxygen gas should you expect? Does that make sense? We're going to decompose this. I'm going to tell you how much you start with. My question for you is, how much oxygen should you expect when you're done? And we've already kind of done stuff like this before in our previous units. I kind of tried to mentally prep you for this scenario here. Because the first thing you need is your chemical equation balanced. And currently it's not balanced. So let's make sure it's balanced first. To do that, I'm going to want to put a 2 here and a 3 here to get the oxygen balanced, and then a 4 for the aluminum. Any issues with that part? I like using ratios then. Here's what I would say. You have 3.34 moles of Al2O3. And what I'm going to do is I'm going to set up a ratio so that I get rid of moles of Al2O3 and I try to convert it instead to moles of oxygen. The only thing I need to know then is, well, what's the ratio? How many moles of oxygen do I have for every mole of aluminum oxide? And the ratio is, well, there's 3 oxygens, due to this number right here, for every 2 of those guys. So this works. And then canceling, well, this moles of Al2O3 cancels with this one. There is no law of conservation of moles. I started with 2 moles on this side right here, and on this side I have 7. This is that Barbie doll analogy again. There's 2 pieces that have a lot of smaller pieces inside them, and as I break them apart, well, now there's 4 of these guys and 3 of these guys. But I'm getting more when I'm done. Does that make sense? So I just need a calculator now. 3.34 times by 3 over 2 means that I would expect 5.01 moles of oxygen. Okay, who might care about this then? I'll give you a couple examples. Car companies. Nowadays, car companies are being asked to limit their carbon dioxide emissions. You guys ever heard of this before? Volkswagen had a big scandal a while ago because they were cheating on this. I have a Volkswagen. If you have a chemical reaction that, say, you know is going to emit carbon dioxide, you then should know, well, how much carbon dioxide will it make? Does that make sense? How much would you expect it to produce after you do combustion? Now, I know this one here doesn't make carbon dioxide, but in a similar sort of way, the question is, how much of your product should you expect based on what you start with? So if I can tell you how much to begin with, hopefully we can start to build some skills where you can make a prediction as to how much to finish with. There is one quantifier that has to go on here, though. We do have to assume that this happens with a 100% rate. But I told you on a previous slide, though, we do assume that, okay? Unless I tell you otherwise, we do assume that it happens all the time. But if I ever show you an example where this is not 100%, where this is, say, 50%, what would you do then? Take your final answer and times it by 50%. Does that make sense? Or if this right here was a 25%, then take your final answer and times by 0.25. But unless I tell you otherwise, we can assume that everything here turns into this here. Let me try some more examples. Here's one. Acetylene is highly combustible and compressible, and it's used in welding. This would be a good example of someone who maybe they need to know how much carbon dioxide are we emitting? Because you can see this combustion example produces CO2. So what I'm going to do here is I'm going to tell you how much acetylene to burn. We're going to burn 3.84 moles of it. So I've got three questions. Question one, how much oxygen are we going to need? Because you guys know that you can't actually have combustion without oxygen, right? That's a requirement. So how much oxygen will be needed for this to occur? We probably have lots, but let's just make sure. And then the follow-up two questions, how much H2O and how much CO2 can be formed? So I can really solve for this one, or this one here. The first problem I have, though, is that I have to have a balanced chemical equation. And this one's not balanced yet. So to balance it, let's see, I should put a 2 here for the carbons. Hydrogen's good already. Dang it. The oxygens are going to need a decimal number. Let's see. Put a 2 here. I need a 4 there. I need a 2 here. That's what, 8 plus 2 is 10. There, not balanced. Everybody okay with that? So here's what I would recommend to start doing then. I would say you have, that clock's not on time anymore, is it? It's still ticking, but it's not on time. Okay, start with this, 3.84 moles of C2H2. And what I want to do is set up a ratio so that I get rid of my moles of C2H2 and turn it into moles of oxygen. All I've got to find now is, well, what is the relationship between oxygen and acetylene? And the answer is, well, there's 5 of these guys for every 2 of those ones. And what essentially happens is this unit right here cancels that unit. So to figure out how much oxygen you need, 3.84 times by 5 divided by 2 means I need 9.60, by the way. Don't forget your sig digs. Moles of oxygen. For any of you guys who did it on your calculator, you got 9.6. It's only 2 sig digs, though. Now, some people would say, hang on. This 5 right here, there's only 1 sig dig there. No, that's an exact number. Like, that's 5.00000. Does that make sense? Can you have half of an acetylene? No, they have to be in whole number increments. So, like, these numbers right here are never part of your sig digs. Now, using that same sort of concept, I can then make, like, predictions of, well, how much water. Right here, I'm going to say, let's say that you wanted to make water. Say the whole point of this endeavor was to produce water vapor. Maybe I would ask you then, well, if you want to make 8.95 grams of this stuff, how much of this should you begin with? I'm kind of working backwards and making a prediction. So, I mean, you can do the exact same thing. Say, well, I have 8.94 moles of H2O is what I want to make. But that's not really what I'm looking for. I want to eliminate that, so I'll put it on the bottom of the fraction. What I really want to know about is how many moles of acetylene are required. And then since it's the same equation, all I need to do is know the relationship. So for every 2 acetylenes, I make myself 2 water vapors. Do we actually have to do any math on this one then? No, because really when you times by 2 and divide by 2, however many moles of this you start with, apparently you get the exact same amount. So I guess you end with that many moles of C2H2 as well. But the only reason why it was the same number is because this was a 2 and that was a 2. We did this in our gases unit, right? We did that exact same concept in gases. Let's try one last example here. You have 2.47 moles of H2O2. This is kind of the question I was alluding to earlier. You're going to burn something, and especially now with carbon taxes, according to Alberta regulations, you're supposed to pay a carbon tax on how much carbon gets emitted. Now, it may not be easy to actually know how much carbon gets emitted by capturing the carbon dioxide, because honestly, if we could capture the carbon dioxide, why wouldn't we just prevent it from going in the atmosphere in the first place? So what you'd have to do instead then is know, well, this is how much I burned. Now I'm going to tell you how much carbon dioxide it should have made. Does that make sense? And then you got to pay your carbon tax on that. So 2.47 moles of C2H2 is how much I've burned. Let's get rid of the moles of C2H2 and figure out the moles of carbon dioxide. The relationship is 4 carbon dioxides come from every 2 acetylenes. That's not good. For every amount of this I use, I make twice as much carbon dioxide. This actually is now becoming more impactful. Before I finish this answer off, let's say that I started with the exact same amount and it gave you 19 moles of carbon dioxide for every 2 moles of fuel. Do you see that would be even worse? Because like some fuels, they give off even more carbon dioxide based on this relationship here. So it's actually good that this one's only 4 for every 2. You know what would be best actually from an environmental point of view? Is if I could find something where it gives off 1 mole of carbon dioxide for every, like, say, 15 moles of fuel. If I could find a fuel that would do this, you know what I'm saying here? That would actually be really good because then rather than emitting more carbon dioxide, I'm actually getting less carbon dioxide than I began with. So, anyways, you just got to double this number, right? 2.47 doubled 4.94. Any questions on that? Well, then the carbon tax works by saying, well, however much you emit, then you need to pay, $1.63 per kilo something. I don't know, kilogram. This is where my next part goes here, though. Although we can work with moles, do we traditionally measure things in everyday life in moles? No, we usually measure things in either liters, grams, concentration of some type, but like measure things in moles is not overly useful. So when the government then wants to charge its tax and say you got to pay $1.63 per kilogram, I can't actually multiply these numbers yet because this number is in moles and I need it to somehow correlate with kilograms. So the next thing I want to show you how to do, if I can go back a slide here, is although we can do mole to mole calculations, it's better if we can usually work with masses because masses is something we usually use in everyday life. Does that make sense? So, which is why I believe this next slide right here kind of talks about that. We don't usually work with moles. A mole is this many molecules, but it's so much easier to use your weight in grams. So here's what we need to be able to do then. You need to be able to find me off your periodic table a molar mass. And if you can do that, then we're just going to add to the concepts we've already learned, and we're going to do some conversions of grams to moles. How am I doing so far? Anybody got questions? Anybody completely lost? It's okay to admit it. Okay. Here's kind of a flow chart then that's going to describe what we're going to try to do. We're going to be given a grams value of some substance. We're going to take that mass and we're going to use a molar mass to get moles. Once we have moles, we can use the coefficients from the equation like we just did in the previous example to figure out how moles of A get you moles of B. And then once you have moles of B, then you're going to use a molar mass and go back and find grams again. It's almost like you have to convert grams to moles, work with the moles, and then go right back to grams again. So let's try an example. Let's say that I give you 10.1 grams of iron. Here's my question. Let's figure out how many grams of copper we would expect to form. But again, I'm giving you an unbalanced equation right now. So before I go any further, I better balance this thing. So we're going to need to put a 2 here a 3 here, and a 3 here. So far, so good? Okay. So I started with 10.1 grams of iron. The question is, how much copper is going to be produced? So do something like this. Take 10.1 grams of iron, and this is the way I like to set it up. I'm going to do a molar mass like this. I'm going to try to eliminate this grams right here using iron's molar mass, which I believe is 5585. Now, I'm actually not going to find this number right now. I'm going to do it all in one swoop. I find this easier myself. But can you guys see how the grams is canceling here? At this point right now, I have moles of iron. Okay. Well, now let's try to get rid of moles of iron and turn it into moles. Oops, that's not right. And try to turn it into moles of copper. This is what we just did on the last slide. What's the relationship between moles of copper and moles of, that's iron, by the way, if you can't read my writing. What's the relationship between copper and iron? 3 coppers for every 2 irons. Okay. Well, now what I've done is I've canceled this iron here, this mole here. I now know how many moles of copper I've created. But again, we don't normally measure things in everyday life in moles. We usually want to measure them in grams. So the last thing I want to do is I want to find a way to get grams so that I can cancel this moles right here. And I need copper's molar mass. Copper's molar mass, I believe, is 6355. And I'm going to do this all in one big chain. So let me see if I can explain one more time where all these numbers come from, and I'm going to show you on the diagram I had on the previous slide here again too. Where's my highlighter? Here it is. I want to go back to this slide for a second here. The first thing you have to do is take grams of substance A and turn it into moles of substance A. And you do that using a molar mass. Well, that's essentially what I did right here. I took these two numbers, and I took grams and I divided by molar mass to get moles. The next thing we have to do then is we have to take moles of substance A and turn it into moles of substance B using the ratio. And that's what I did right here. Still with me? And then for the last step, I don't want moles though. Moles is not a really effective everyday life tool to use. So for the last bit, I reused a molar mass and I went back the other way. Now, here I believe I had to divide by a molar mass, but when I go back the other way, you then have to times by a molar mass, which is why here I'm timesing by the molar mass, whereas here I'm dividing. Now, I prefer to do this all in just in one big row because I found that it's just easier to not round then. So the last thing you should do then is take 10.1, divide by 5585, times by 3, divide by 2, and times by 6355, and in one big line of work, I got 17.23 or so. That's my answer. Okay, what does the 17.23 mean, though? Well, look at all the units that didn't cancel. This iron canceled that one. This gram canceled this one. This mole canceled this one. This mole canceled this one. The only 2 units that didn't cancel were grams from right here and of copper. And isn't that what we were asked to solve for? We were asked to solve for grams of copper, so now I have that. One last step, though, I do need to do sig digs right. So I got to look back through all the work I did right here and figure out what limits me for sig digs. The 2 molar masses have 4 sig digs. The grams number right here had 3 sig digs. And these numbers right here are not included because those are exact values. So 3 sig digs means our final answer is 17.2 grams. There. Now I know how much to expect. Does that make sense? Well, let me go back to my original question to start the class. If I can give you a number here and tell you how much to expect, why can't I work backwards then and say, well, if I want to make a certain amount, here's how much I should start with, right? Because the very, very first question I started class with was, let's say that you want to make 20 grams of silver. Now, is there only one way of making 20 grams of silver? No, there's probably tons of ways. But I mean, a great way of starting would be to say take silver nitrate and add it to, say, copper. And the reason why I would choose to do that is because it's going to give me copper nitrate and silver. Look, now I finally found a way to get silver by itself. But here's some practical questions. Did it have to be silver nitrate? Could I have done this with silver chloride? Probably. Did this have to be copper right here? Well, let's say I made it zinc. Well, then wouldn't this make it zinc chloride and silver? That's not us, is it? No good. Do you see how I've managed to find two different equations? Both of these equations produce silver. Does that make sense? So there's not necessarily one right answer. Well, if you want 20 grams of silver, if you want 20 grams right here, the second half of my lesson now is, well, let's figure out how much of this you need. So why don't I go, I think I've only probably got a few examples left, right? I hope. Just one example left? Okay, so let's try this last example and we'll call it a day. So here's the question. You're going to use this chemical equation to produce some silicon. And again, you might ask the question, well, why do you need silicon? Well, if you don't know, silicon is used in computer chips. So here, I want to try to get myself some solid silicon. Okay. And for whatever reason, I've discovered that I need 9.3 grams of silicon. So there's the point of my equation. I want to make exactly 9.3 grams. Not more, not less. I want exactly that amount. Sound good? So the question is, how many grams of magnesium do you need? But more than that, a follow-up question is, how many grams of silicon tetrachloride will you need? Right? I need to make sure that I combine the exact right dosages when I start, so that when I'm finished, I get exactly 9.3. So let's try this here. When I write up my line of work, I would start with this, 9.3 grams of silicon. Now, grams is a fantastic unit to use in the real world, but in chemistry, we sometimes need to convert to moles. So to convert to moles, I like doing this. I put a mole over top of a gram so that it'll cancel grams. And I don't have this memorized. Someone help me out. What's silicon's molar mass? 2809. Thank you. Okay. At this point here, I've now canceled the grams number. And I'm into moles. Perfect. Well, I no longer want to work with moles of silicon. I'd rather know information about moles of magnesium. So in this next step, then, I need to know, well, what is the relationship between magnesium and silicon? And I didn't actually balance the equation yet, did I? So let's go balance it. I think I need a 2 here to balance the chlorines and a 2 here. So, in a way, I now know my recipe. My recipe says that for every 1 silicon I want to make, I better bring 2 magnesiums to the party. Okay, now that's how many of them I bring. For every 2 magnesiums I bring, I get 1 silicon. But the final question is, sure, you're bringing 2 magnesiums. How heavy is a magnesium? So your last step, then, is to reuse a molar ratio and use magnesium's molar mass, because a magnesium weighs 2431. When you're done, if you can kind of follow this, these grams will cancel, this silicon mole will cancel here, and this mole will cancel here, leaving you with grams of magnesium. So even though you need to bring 2 molecules of magnesium for every 1 silicon, because silicon and magnesium weigh different amounts, this will now tell us how much mass to bring right here. So calculate it. 9.3 divide by 2809 times by 2 times by 2331. I got 16.6. 16.6? No? Oh, I see where I messed up here. Thank you. That's 9.3. 16.1? 16.1. 16.097. Okay. With SIGDIGs, I think I only get 2. So how much magnesium should you bring? Bring 16 grams. Okay, but to make the silicon, yeah, you need 16 grams of magnesium, but you're also going to need some silicon tetrachloride. So we can do the exact same work and try to figure out how much silicon tetrachloride to bring as well. And it may be more or less. It really depends on weight. Now, here's the great thing. You guys are going to like this part here. Much of the work remains the same. Watch. I'm still starting with 9.3 grams of silicon. And I still know silicon's molar mass is 2809. That part hasn't changed. And when I'm trying to do a conversion, I still know that I need 1 mole of silicon. Like literally the first half of the equation hasn't changed. So I'm going to use a different color here. What does change though is, see how right here I wanted to find magnesium? Well, in this example here, I want to find silicon tetrachloride. And it has a different relationship. This was a 2-to-1 relationship. This guy was a 1-to-1 relationship. So that changes slightly. And then the other thing that changes is that the molar mass that I'm going to use here is no longer 2431. That's magnesium's molar mass. I got to know how heavy silicon tetrachloride is. So that's 2809 plus 3545 times 4. I calculated a molar mass of 169.89. Okay, so again, I really like to encourage kids to be able to learn how to unit cancel. I think it's a useful skill. This grams cancels this grams. This silicon cancels this silicon. This mole cancels this mole. I should have written a mole here. This mole cancels that mole. And when I'm done, the only units that I haven't canceled are grams and silicon tetrachloride. So now just... Do you guys get, by the way, why I think it's better to do this just all in one big row rather than do it in like small calculations? Because you could do this times this, stop. Then times by this, stop. Then times by this, stop. But to me, I feel like if I can show you to do it all in one big section here, it's much more efficient. Divide by 28.09, times by 1, divide by 1, times by 169.89. So I have an answer of 56 grams. Anybody else get that? Now, this sometimes perplexes some kids because they're like, hang on a sec here. You're telling me that I need to bring twice as much magnesium as silicon tetrachloride, right? Because isn't that what this says? This 1 and this 2 right here means that for every 1 silicon tetrachloride, you better bring 2 magnesiums. And yet the masses, I'm bringing less magnesium. Why is that? And silicon tetrachloride is much heavier. Does that make sense? And so because silicon tetrachloride is very heavy, you're going to need to bring more of it because of its weight. Does that make sense? Wait, last thought then. Sometimes when you do a chemical reaction, you make another byproduct. So I now figured out how to make my silicon. And when I make my silicon, if I bring 56 grams and 16 grams, it should then, in theory, make me my 9.3 grams of silicon. But as a final question, I could ask you, well, how much of this stuff should I expect with it? Because look at the masses. When we begin right here, there's about, 72 grams collectively amount of product to begin with. Sorry, of reactants to begin with. And only about 9 grams ends up being the silicon. Where's the rest of the mass? Here. Let's see whether we end up getting a large amount of magnesium chloride as a byproduct with it as well. So again, this is very, very repetitive. You're still starting with 9.3 grams of silicon. You're still using the molar mass of silicon. That hasn't changed. And on the bottom, there's still 1 mole of silicon. But let me change colors now, just to help illustrate the difference. I can do the same work now, and instead I'm going to look for my magnesium chloride. So there are 2 moles of magnesium chloride for every 1 silicon. The only difference now is that when I use a molar mass at the very, very end here, I use magnesium chloride's molar mass. So 35, 45 times 2 plus 2431. I got a molar mass of 9521. So again, if you can follow my work here, the grams cancels this grams, the silicon cancels this silicon, the moles cancels the moles here, this moles cancels that moles there. The only thing that didn't cancel then is grams of magnesium chloride. So run the numbers through. Divide by 2809 times by 2 times by 9521. I got an answer of 63 grams. I want to show you one more thing. This is really cool. Law of conservation of mass makes sense, by the way. 56 plus 16 equals 62. 63 plus 9.3 also equals 72. I know there's an extra 0.3 on here, but if you were to make it so that they're at least all to the nearest whole number, to the nearest whole number, this is 56. To the nearest whole number, this is 16. To the nearest whole number, this is 63. To the nearest whole number, this is 9. Before we started with 72, afterwards we started with 7. We finished with 72. Law of conservation of mass holds. Does that make sense? So quick summary and then I'm done. Stoichiometry is really powerful then, because it allows you to do a couple of things. One, it allows you to make a prediction. If I tell you what you're beginning with, you should be able to predict for me what you're going to end with. Make sense? That can be useful. Right? If I were to combine this and this, now you know how much to expect. But better than that, if I tell you I want 20 grams of silver, you can now reverse engineer this and work backwards and figure out how much to begin with. So if I go right back to my first slide just to finish off this thought, let's say that you want to end with 20 grams of silver. Okay, the first thing you got to do is find an equation that somehow produces silver by itself. And hopefully I kind of explained to the idea that it didn't really matter that this was a nitrate right here. It didn't really matter that this was a chloride right here. That doesn't really impact the point of the question for what we have, right? So if I have silver nitrate in my lab, I'd use it. If I don't have silver chloride, then find something else, right? And then the way you'd do is you'd take 20 grams of this, you'd divide by silver's molar mass, you'd use the ratios in front to figure out how much of this you'd need, and then you'd reuse a molar mass to get grams. And now you'd know how Walter White in Breaking Bad is able to predict exactly what to start with, so that if he knows exactly what he's starting with, he can then tell you how much exactly he's going to finish with. Does that make sense? Okay, cool. We're going to do a lab on this next week, Tuesday, to try to prove this point. So I've got one more set of notes on Monday we're going to do between there, though. So, you guys have any questions of me? Life is good? Sweet. Okay. You've got 15 minutes, I guess, to do stuff.